Hello, welcome to the series of linear integrated circuit. And today we will discuss about the integrator, that is a kind of linear operation integrating of input signal, that is a kind of linear operation. And in previous classes we have seen different circuits: inverting amplifier, non-inverting amplifier, subtractor, summing amplifier, etc. So in this circuit, in inverting amplifier, we will try to modify the component of feedback, and we will get a different kind of application, that is the integrator. So here we can see in feedback we have used a capacitor. Capacitor is connected between this inverting terminal and output terminal. So we have used a capacitor as a feedback component. So let's see how we can analyze this circuit. So integrator is basically, we can write here, can write an integrator is a circuit. An integrator is a circuit in which the output voltage waveform is the integral of the input waveform. Integral of the input voltage waveform. And what is the important point regarding this integrator? The feedback we will use capacitor. In feedback we will use capacitor. So now we can make it circuit. We will draw the circuit diagram of it. So this is the symbol of op-amp. This is the output terminal that is taken at 6 number point. We have two inputs. One is inverting terminal, second is non-inverting terminal. Let's say this is pin number 2 and this is pin number let's say 3. Here the voltage is V2. This is the voltage V1, that is non-inverting, V2 is inverting, and it will amplify the difference of these two signals. And we will use a feedback here. So here, instead of connecting feedback resistance RF, we will connect capacitor, and let's say this is CF. Now we have connected a capacitor here, and this is the resistance R, and we will connect a voltage source at inverting terminal. So this can be called as input voltage V in, and non-inverting terminal is grounded. So this become the circuit of integrator. Here we have two DC supply. This is plus VCC. This one is minus VCC. So what is the main component? That is the main changes in inverting amplifier. The only change is that we have used a feedback capacitor. Here we have used a feedback capacitor. So now we can analyze its diagram. We can analyze its circuits to get the output. So here we can write the node A. Which one is node A? This is inverting terminal. This is node A. So we have a junction where currents are meeting. So let's say the current flowing through this branch in this branch is IR. Current going inside of this op amp is I, that is always 0 because of infinite resistance. And here the current is, let's say, IC. So we can write here at point A, apply KCL. So at point A, what we can see, IR will be I plus IC, and this I value is 0 because of infinite input resistance. So we can write simply IR is equal to IC. Now we will write the values of these currents. So here, here from equation 1, we can write here from equation 1, the current flowing through this resistance R is equal to current flowing through the capacitor C. So what will be the value of IR? IR is basically input minus this voltage V2, input minus voltage V2 divided by this resistance R. So here we can write here like input minus V2 divided by resistance R. That will be the value of IR. And what about IC? IC, we know that the charge in capacitor Q is equal to C into V. Here we can write CF into V. So this charge, now we can write the current is d by dt of this Q charge. So we can write d by dt of CF into V. So here we may have this constant CF out of this term d by dt of V, and this V is the voltage difference. This V is the voltage difference. So IC can be written as CF into d by dt of, what will be the voltage difference? Voltage difference is simply, as we have seen earlier, this V2 voltage minus this output voltage, V2 minus V output. So we can write here V2 minus V output. So this is the value of IC and this is the value of IR. Now we can equate these two values. So what we will get? We are going to equate these values. So we will get here IR is equal to IC. So this become V input minus V2 divided by R is equal to this is CF into d by dt. This is CF into d by dt of V2 minus V output. So this will become the current equation. So now we can write here V1 is equal to 0, since V1 is grounded. This V1 is grounded, so V1 is equal to 0. So by virtual ground concept, we know that whatever voltage present at non-inverting terminal, that will be automatically considered as inverting terminal voltage. So this will become V1 is equal to V2 is equal to 0. So now we can put this V2 is equal to 0 in this equation 3. So by putting V2 is equal to 0 in equation 3. So what we will get? We will get here V input minus 0 divided by R is equal to CF into d by dt of 0 minus V output. So now we are going to simplify this equation. So this become V input divided by R is equal to CF d by dt of minus V output. And be remember here input is connected at inverting terminal. So whatever output we will get, that will be negative. That will be negative. So this become the equation. Now integrate both of the sides. Integrate both sides. So this will become integration from 0 to t, that is V input divided by R. So this will become CF. Integration and differentiation will cancel out both the sides. So this will become simply minus V output. And one more constant will be added here, that is A. So this will become V output is equal to minus 1 upon R into CF. Then we have integration from 0 to t, that is V input into dt, V input into dt integration. So this will become dt. So V input into dt plus a constant A. Plus a constant A. So this become the final output equation. This become the final output equation of integrator, where we can see the output is the integration of this input signal, and this is the constant. And we have applied this, we have seen negative sign here because input is applied at inverting terminal. So there is a phase shift of 180 degree between input and output voltage. So what is A? A is simply the integration constant. We can write here A is simply the integration constant. So the output is simply the integration of input voltage V input. So this is all about your integration. We remember in this integration circuit, integrator circuit, we have used a feedback. Feedback component is, this is CF. The feedback component is a capacitor, and by connecting this capacitor we have analyzed this circuit, and we are getting V output as minus 1 upon R into CF, integration from 0 to t, V input into dt plus A. A is the integration constant. So thank you for watching this video, and next video we will see about the differentiator of differentiator operational amplifier. In this circuit we will use capacitor at the point where resistance is connected. So we will see that how we can analyze the differentiator circuit.